Hi, this is Tom. Today we're going to go over the material found in our fourth class in the Science and Christianity series. We're going to go from Newton to atoms and thermodynamics. So last time we talked about how the church was instrumental in founding universities all across Europe and encouraging broad questions about God's creation. These were general purpose universities, and they helped establish modern science. We talked about how people coming out of those universities were able to show that the sun was at the center of the solar system and that the earth rotated about the sun, which overturned Aristotle's view. And we talked about how science grew up out of careful observations and experiments, disproving Aristotle's speculations about gravity. We talked about important concepts having to do with motion, like position. Position, of course, refers to how far away something is from a given point and in what direction. We call that a vector. We talked about how velocity is how fast we're going in a particular direction, also a vector. And we talked about acceleration, which can be discussed in terms of being a vector as well. It's how fast velocity is changing in a given amount of time. We talked about the concept of relative motion, so that, for example, if you had a boat moving at a particular velocity and you had something inside the boat moving relative to the boat, that the apparent velocity relative to someone on the shore would be the motion of the boat plus the motion of the object relative to the boat. And we talked about the conservation of momentum. Remember that momentum is actually velocity, which is a vector, times mass, which is kind of like the weight of an object. And we talked about how Francis Bacon spread the scientific method, how he formalized it and then he popularized it. Then Newton took the stage, and that's kind of where we reached last time. So, what did Newton actually do? Well, starting in 1666, Newton came up with the following. This is just kind of a summary. He came up with a complete theory about motion, and that motion could be simple motion in a straight line, it could be complex motion in a circle, or any curved path. He was able to fully explain all observations made to date about motion. And he invented a new type of math, we call that math calculus, which turned philosophy into numbers and engineering. That's kind of poetic and descriptive more than precise, but it's hard to fully explain in this course what calculus is. I'll only say that Newton could not have been so general in his ideas about physics and motion in particular, if he had not come up with calculus. Newton discovered that objects fall on Earth for the same reason heavenly bodies orbit one another, and we'll talk more about that in this class today. And he used physics and calculus to analyze all the work that Kepler had done. Remember, Kepler discovered that the planets move in elliptical orbits around the sun, but didn't know why. Newton used what Kepler had done to come to understand the specific nature of gravity, and we'll talk about that today also. So, the fundamental view of motion given to us by Newton is expressed in three simple laws. Okay, so they're often referred to as Newton's three laws, and together they can describe, along with math, they can describe all motion. Now, I just want to say, kind of as a, you know, um, um, comment ahead of getting into it, that they're amazingly brief and insightful, and simple, given how much power comes from them. Okay, it's kind of like, as we said in an earlier course, from tiny acorns, mighty oak trees grow, along with the math that Newton invented, which was also quite ingenious. Okay, well, all of these laws, let's kind of do an overview here before we talk specifically about each of them. All of these laws involve forces. Now, we might think of a force as a push or a pull, but you know that's kind of a descriptive definition. It's a little vague for doing science and making precise observations and measurements and that kind of thing. So we might ask, how could we turn this basic intuitive idea into something really precise? And the earlier thing we learned in the last class, and we briefly reviewed today, is, conservation of momentum. It turns out that can help us give a good definition for force. And now this is a little bit subtle compared to what we've discussed so far, but if you can follow this and understand it, then you can understand really the foundation of physics. Okay, so I'm going to give this a stab, and hopefully you'll understand it on, kind of a conceptual level in any case, but I'm thinking you guys can get this. Okay, so remember again the idea about conservation of momentum. A basic illustration of it is if we have any two objects that interact. Let's say the two objects start with momentum 1 and momentum 2. So we'll call them objects 1, or mass 1 and mass 2, and they're going to start with momentum 1 and momentum 2. Now remember, the momentum is expressed by these arrows. The length expresses the size of the momentum, and the arrow, the direction of the arrow expresses the direction of the momentum. So if we take the starting momentum for each of these objects and add them up, we kind of see that in the upper left-hand corner. We get that red arrow in the upper left-hand corner, like before the two pool balls collide or whatever's going on here. Okay, and the idea about the conservation of momentum tells us that after they collide, the sum of their momentums is going to also add up to the same red arrow. Even though the individual balls are going to be going in a different direction with different momentum after they collide, say, they're still going to have the same total when we add the little arrows together geometrically. Okay, so we know momentum is going to be conserved for the two balls together if we add the momentums together. But what about each one individually? Well, the first ball, the first mass, starts off with, mass 1 moving at velocity 1. That's expressed by the arrow given the first mass, the first ball on the left. And it ends up with a different velocity, and so its momentum is its mass, which didn't change, times its new velocity, or its final velocity after the collision. That's represented by the arrow on the right. So even though there's a conservation of momentum when we add the momentum up for the two balls, the individual balls do have a change in momentum. Okay, we could say the same kind of thing about each one. Like the second ball starts off with momentum, a momentum that's equal to its mass times its initial velocity, and it ends up, the second mass, with a final momentum of its mass times its final velocity, just like ball number one. And again, its momentum changes in the collision. So what is the change in momentum for each one of these balls? What causes the change, and what determines how big that change is? Well, as far as what causes a change, we could kind of think intuitively. It's some kind of push or pull. The thing we're trying to get at. There's a force involved. There's some kind of push. There's some kind of push or pull involved, and the change is also related by not just how big a push or pull is causing the change, but also how long that push or pull occurs. Okay, so in order to come up with a good way to look at this change momentum that occurs for each ball and involves the push or pull, which we're going to call force, as well as the time, we might want to think about the change in velocity for each one of these two as being really the same thing as the average acceleration for each one times the time during which the acceleration occurs. So a change in velocity, remember, the change in velocity is equal to the acceleration times the time. We talked about that in the prior class. So that means we can talk about the change in each one of these balls as being the change of momentum as being its mass times its acceleration times the time when the acceleration was occurring. So both change one and change two, for each of the balls could be expressed that way. Now, again, thinking about, the change momentum that each ball experiences as like the size of the push or the pull, which we're going to call a force, times the amount of time it happens over, well, that makes it seem like the push or the pull, the force, would be defined as mass times acceleration. Because when we look at those expressions for the the change in momentum for ball one and ball two, they both involve mass times acceleration times time. So we're saying intuitively that a force, the change in momentum would be caused by a force applied over a particular period of time. So when we can just look at what we've thought through there, and we can say, well, the force must be mass times acceleration. Now, this is just a definition of force. This is how Newton decided to call a force. This is how Newton decided to define a force as mass times acceleration. And that's Newton's second law. It's a definition. Newton, and force is a vector and acceleration is a vector. Newton said force would be equal to mass times acceleration. Notice it's very similar to momentum, which is mass times velocity, but instead it's per time. So we could also think of force as the rate of change how fast momentum is changing in a given amount of time. But in any case, we can kind of see how it makes sense to define force as mass times acceleration. Okay, so that's nice. We can now talk about the change in momentum in any object as being, basically the force times the acceleration. Okay, or I'm sorry, the mass times the acceleration times the time. And we can talk about the force as being the mass times the acceleration. So we could talk about the change in momentum as being the force times the time. So can we gain any further insights from the conservation of momentum? Well, we know that the momentum doesn't change, between before and after the interaction of these two pool balls or whatever it is. So that means that the change in momentum of the first pool ball has to be numerically the opposite, or mathematically the opposite, as the change momentum in the second pool ball, because that's the only way that the total momentum is going to end up being the same, right? So, and when we're talking about, when we're talking about the total momentum, we mean, adding the little arrows up geometrically. So if we look at the change in momentum in each of the objects and we add up the changes together in the same way we add the total momentum, either before or after, the change has to exactly cancel out. Meaning, the change momentum of the first object will be the same size as the change in momentum in the second object, but they will actually be pointed in different directions. Because if you didn't have that, you would end up with a different total momentum. Okay, so that means, since the changes are the same size but in the opposite direction, that means that the force times the acceleration of the first object has to be the negative of the force times the acceleration of the second object. Okay, that means that the forces during this interaction are kind of equal and opposite. So they're the same size forces, but they're pointing in exactly the opposite direction, and that makes sense, because if pool ball 1 is pushing pool ball 2 to the southeast, then at the same time pool ball 2 must be pushing pool ball 1 to the northwest. Okay, and that is Newton's third law. For every action, there is an equal and opposite reaction. This has to happen in order for there to be conservation of momentum. So far we've gotten the second law out of the conservation of momentum, and now we've gotten this what's always called Newton's third law, that for every action there's an equal and opposite reaction out of the conservation of momentum also. Okay, well, that only leaves us with the first law. And the first law, we could read on the left, says an object remains at rest or in motion unless a force acts on it. Well, this just comes directly from applying the second law, which says that force is mass times acceleration. If there's no force, then there can't be any acceleration, and a change in motion means there has to be an acceleration. So no force, no acceleration, no change in motion. Okay, so it comes right out of the second law. And if there is a force, right? If there is a force, there must be an acceleration. So a force necessarily causes a change in motion. And so the first law is really equivalent to the second law. But historically, Newton, the foundation of Newton's understanding about motion is stated in these three laws. Okay, once again, I want to, just touch on the idea that force is a definition, but it's a good definition that was motivated by our understanding of the conservation of momentum that Descartes and Huygens had discovered earlier, and our common sense notion about pushes and pulls. Okay, and so Newton was able to come up with a well-defined mathematical definition of a force that he drew out of conservation of momentum. And it turns out that's going to work really, really well, and we're going to see that. Okay, well, let's look at an example of the first law applied. Okay, remember the first law says that if there's a change in motion, there must be an acceleration. Now, like we all do, Newton knew that things fell. So suppose an apple falls. What does the first law tell us? If an apple falls, that means it's going from 0 to picking up velocity as it goes toward the ground. What does that mean? The velocity is changing, so we have an acceleration. But an acceleration implies a force. The force on the apple, there must be a force on the apple. That's what the first law tells us, and it must be the same as the mass of the apple times the acceleration the apple is experiencing. So that's what the first law tells us. So we've discovered gravity. Yay. Well, no, not really. I mean, people have known about gravity a long time. So we're just giving a name to the force that causes an apple to fall from a tree now, but let's call it gravity. We can just basically say that gravity is the force. Okay. Well, let's see if we can apply the second law. How strong is gravity's pull? So, Galileo found that acceleration was constant when things were falling, whether they were rolling down a ramp, kind of a stretched out fall, or whether they were falling from a tower. He was able to figure out what the rate of that would be. And I can tell you that when things fall, if we ignore the effect of the air on something, gravity causes things to speed up by 32 feet per second each second. So that's the acceleration due to gravity. And so we know that the force caused by gravity on an apple would be the mass of an apple, whatever it is, times 32 feet per second. And that tells us how fast the velocity is going to change. Now, if we get a little fancier on the math, we could actually say that the velocity of the apple at any particular time would be the starting velocity, which is 0 if it was hanging on the tree not moving before, plus the mass times the acceleration, which is g in this case for gravity, times time. And we could also use calculus, and we could tell how fast the position of the apple was changing. So we could come up with a fairly simple algebraic type expression that gives us the position. So from applying the first two laws and the idea that gravity is an acceleration, causes an acceleration, we can come up with an exact description of the velocity and the position of the apple at any given time from the time it's breaks off the apple tree. Now Newton made a very key observation at this point. He realized that, or he wondered if perhaps the same thing that caused an apple to fall might not also cause one heavenly body to orbit another. For example, the moon to orbit the earth, or the earth to go around the sun. His idea was that if you threw something really fast on Earth, that it would kind of arc down and hit the ground eventually. But he wondered if you threw it even faster, what would happen, and it would go further before it arced down and hit the Earth. And so he thought logically, if you throw it fast enough, it would arc down no faster than the surface of the Earth curved away from it, because the Earth is not flat. So he figured that if you had enough horizontal velocity, that gravity would only pull something down at the same rate that the Earth was curving away underneath it. And he thought, well, gee, that's probably what's happening when the moon goes around the Earth. And you know what? Newton had something there. So let's think about how Newton analyzed the situation to kind of figure out the nature of gravity. The second law tells us that the force is the mass times the acceleration. So we can know the force on any object when we know its acceleration. Now, likewise, if we know the velocity, we can, at different times, right, we can calculate what the average acceleration is between any two times, because acceleration is just how fast the velocity changes in a given amount of time. So calculus can do even better than that. It can calculate the exact acceleration for each and every instant. If we know what the velocity is all the time, which we do for a falling apple, or for even an object we throw on Earth, if we know what the velocity is at a particular time, that expression we had a few slides back, then we can use calculus to figure out exactly what the acceleration is at each and every instant. And the acceleration, if we know the acceleration, we can put it into our definition for force, and that gives us the force. So we could even say that if we know the position at any particular time, calculus can give us the velocity at a particular time, and then from that, calculus can give us the acceleration. So we can kind of get a complete picture, and of course that gives us the force. So knowing the position at any particular time, we can get the velocity and the acceleration and the force at any particular time. So this is all what the math can do. And so Newton is saying, hey, so given the apple falling to the earth, or given something that's thrown on the earth, or something that has some particular starting velocity around the earth, I can figure out what path it's going to move in, and I can figure out what force must be at work, what force must be at work if it's moving in a particular way. And so that's what he did. He used the well-known fact that he knew where the moon was at any particular time compared to the Earth. It was easy to observe the moon. It was known how far away the moon was. And so given the fact that he knew where the moon was, the position of the moon at any given time, he was able to understand the velocity of the moon at a particular time, and from that he was able to understand the acceleration of the moon at a particular time, and from that he was able to understand what the underlying force must be at any particular time. And here's what he found, and this sounds obvious to us in this day and age, but he found what we are very comfortable knowing these days, which is the force that caused the motion of the moon pointed straight at the center of the Earth. Okay, now likewise, Kepler had figured out the motion of the planets around the sun, but he didn't know why. So Newton looked at the positions of the planets around the sun and applied this same kind of analysis, and he was able to also describe the forces on the planets that would cause such motions. And those forces pointed directly at the center of the sun. Now the forces were not constant. As planets move around the sun, sometimes because the orbits are elliptical, sometimes they're a little closer, sometimes a little further away. So when they're further away, there's actually a little bit smaller force on them, and when they're a little closer, there's a little bit bigger force. Okay, so the force due to the sun, which we call, the sun, which we say is the sun's gravity, on those planets, it's not constant. if it's the same kind of thing that causes apples to fall on Earth, or caused a ball to drop from a tower when Galileo dropped it at more or less a constant rate, or also a ball rolling down a ramp. Why does gravity seem constant if it's not constant? If it's the same thing that causes the planets to orbit, but it's not constant there? Well, the only reason is because Newton found that gravity, the size of the gravity, pretty much depended on how far you were from the center of mass of an object. So because the Earth, it has a radius of about 4,000 miles, we're really not changing our distance from the center of the Earth very much. When we, a ball's not changing its distance from the center of the Earth very much if you just toss a baseball in the air, or if an apple drops from a tree. So it seems like the actual force is constant, 32 feet per second. But if you go out in space and you talk about the moon orbiting the Earth, or then the distance of the moon from the Earth does vary a little bit from one time to another during the month, or the position of a planet relative to the sun does vary a little bit, and so it can be a little closer, a little further from the sun, and so is the force. And Newton was able to use his math to figure out this relation, and the relation was what physicists call an inverse square force. In other words, if you double the distance between two things, the force of gravity attracting them drops by a factor of 4, or 2 times 2. If you triple the distance between the two things, the force drops by a factor of 9, which is 3 times 3. So that's what it goes according to the opposite of the square of the distance between their center of mass. And yet this same force that causes the motion of the planets around the sun also describes simple things like apples falling from a tree on the Earth, or they describe the path a baseball takes if you throw it from center field to second base. And because it's the same force, it has the same nature, whether on Earth or in the heavens. This idea came to be known as Newton's universal law of gravitation. Okay, and the genius of it, in part, is because Newton was able to see that these very different sorts of examples of gravity were still examples of the same basic thing. So when physicists talk about these kinds of things, they talk about unifying. When you take two things that seem very different in nature, and you're able to show that they're really the same thing, physicists say that you unified those two things. So Newton unified motion on Earth with motion in the heavens, completely different, than what Aristotle thought, and that's what's called Newton's universal law of gravitation. At this point, it's worth looking a little more closely at the expression Newton came up with that described gravity. We don't have to worry about the math too much, but I just want to look at this formula for the force due to gravity, this big F over here on the left, and it says the big gravity is equal to this big G thing, which I'm going to talk about in a second, times the mass of one object times the mass of the other object, divided by the square of the distance between the two centers of mass. So the big G thing is called a constant of proportionality. It's the same whether you talk about the force of gravity between the Earth and an apple, or between the sun and the Earth. Okay, but Newton didn't know what that exact value was. Okay, um, he he um, he had no way to know exactly what it was. So, like if an apple falls from a tree, you know the mass of the apple, and you know the distance between the apple and the center of the earth, but you don't know the big G, and you don't know the other mass involved, which is the mass of the entire earth. You know, so eventually someone figured out an experiment that would allow them to measure what this G was, and so they set up, this really careful experiment where you had two big lead balls, and they were kind of fixed, and you had these two little lead balls connected by a lightweight rod, and they're labeled the little M, and they're hanging on a single fiber, that suspends them from some kind of supporting platform above, and they're and the fiber twists just the least bit because the little masses are attracted to the big masses. Now, gravity is such a small force when you're dealing with objects that we could actually move around and things, but this particular way of trying to measure the size of the force was very sensitive, and so it actually was able to pick up the slight twist that would occur in the fiber because the little masses were attracted to the big masses. And this whole thing was enclosed in like a little building to isolate this scientific equipment from the outside, and so there would be no influence of any kind of breeze or anything on it. And there were actually these little telescopic lenses that looked inside so that you could measure the size of the twist, because there was a little scale that they could read off and see how big the angle was. And then from that, they could figure out the force. And from that, they were able to figure out, since the little masses and the big masses were both known, then they could figure out what this constant was in Newton's expression for gravity. And then once they did that, they were able to weigh the Earth, because once you know what big G is, and if you know the force, we know the force because we know the size of the acceleration that causes the apple to drop the Earth. From this, now we know all the things in that expression except for the mass of the Earth itself, and so this enables us to weigh the Earth, which is pretty cool. Um, the um, the remarkable thing about this G in the formula, and this is an ongoing topic of discussion in science today, is it's very, 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 very small. It's so gravity is actually kind of a weak force. Now, we may think of gravity as a strong force. If I jump off a building, um, I'm going to have some serious consequences because gravity is strong enough to do me some serious harm. But another way to think about gravity is that it takes the gravity of the entire planet Earth, the attraction of the entire planet Earth, to hold us down to the ground. Or imagine you take a cheap magnet and put it on your refrigerator, or we could think about putting it on a refrigerator. Well, the cheap magnet is holding onto the refrigerator more strongly than the entire planet Earth is attracting that magnet to the ground. Otherwise, it would fall. So you can kind of see how gravity is a relatively weak force. But Newton figured it out. He figured out one single expression that would describe all all acceleration due to gravity, and also unified the motion of the heavens as being an example of just the force of attraction caused by gravity. And once you measure the Earth, you can also turn it around and you can say, well, how massive must the sun be if it causes the Earth to move the way it does around the sun in a given year? So pretty cool. Um, Compared to Kepler, Newton came up with a really good explanation for why the planets moved around the sun. But there was still something Newton didn't like, which is how did gravity really work? So he was able to describe it in a very precise way using math. He was able to describe it, but the sun and the earth don't touch. How did the sun cause the earth to move around it? How did the sun exert a force on the earth that would be just right to cause the earth to curve around the sun? And likewise, how the earth cause a force on the moon that caused the moon to keep moving around the earth instead of just flying off. And I mean, it's an idea that Newton called force at a distance. He knew that there was a force operating even though these things didn't touch. There, which sometimes forces that happen when things touch are called mechanical forces or contact forces. But Newton saw that there was a force, but he couldn't understand how there could be any force if the things didn't even touch. So he really felt like this action at a distance idea was a real perplexing thing, and thought that somehow it was wrong. Okay, and we will find out later that even in understanding the limitation of his understanding, Newton was right. But that was something Einstein would come up with many years later. Okay, so we see how Newton was able to take these simple laws of motion, and he was able to figure out the motions of the planets around the sun and the moon around the earth, and that was one and the same type of thing as when you throw a ball on earth and it falls to the ground, or an apple drops from a tree. We can also look at that second law, F equals mass times acceleration, and we can think of it in the opposite way. We can think of if we have the force, we can get the acceleration. So if F equals ma, that means A is F divided by m. So if we know the forces acting on an object, we can know the acceleration of the object. And again, using calculus, kind of like before, if we know the acceleration, then calculus can run in the other direction and tell us the velocity. If we know the acceleration at any point in time and we know the starting acceleration, we can figure out the acceleration at any point in time. And if we know the starting situation and we know the velocity at any point in time, we can find the position at any point in time. So once again, starting from either end of this formula, we get a complete description of the motion for any object or any particle. Pretty amazing stuff. Well, as an example of how we might make use of this, let's go back and consider that pendulum of Galileo's, when something is basically rocking back and forth. In this picture, the something would be the thing labeled M. Okay, and there would be several forces on this mass. There would be the string that was preventing the mass from falling, whatever it was swinging back and forth on, or the rope, whatever it is, and that would be what we call a tension force, and it would be pulling in the direction of the string. In the picture, it's labeled F sub t. And then there would also be straight down, that red arrow that goes straight down and says W equals mg. That's the force of the weight of the mass, which is the same, or the weight of the object, which is the same as the mass times its acceleration due to gravity, or g. So you have that arrow going up and to the left. That's the force of the tension on the string. You have the arrow that's going down, which is the weight of the string. And if we analyze the motion of this mass, just from these forces alone, we can explain Galileo's observation about why the rocking back and forth pretty much takes the same amount of time, even as a pendulum loses steam and the arc gets smaller as it moves back and forth. We can also sketch. We can like make a little graph if we want. We can talk about how far the arc is swinging back and forth, what the size of the arc is over time, and we will find out that we get this. We get a graph that looks a lot like a wave on the right. And although eventually a pendulum kind of winds down and loses steam, you know, if it's a nice heavy mass that's not much affected by slight resistance of the air, you know, and it starts off kind of swinging back and forth slowly. We would even find that the amplitude doesn't change very much from time to time, and it would almost look like, you know, a perfect little wave that would seem to go on forever, even though eventually it would wind down. The same three laws of motion applied this way helps us fully analyze and understand everything that Galileo did with pendulums. Okay. Now, if we look at the little graph down below and to the right, does that remind us of anything? It is kind of wavy, right? And maybe if we looked really hard, we could even see a guitar string. Well, it turns out that there are a lot of waves out there, and they are very related to the same math that's going on here, and we'll be able to analyze those things too, and we'll talk about that in a second. But let's talk about how Newton's laws applies to something like a piston. A piston is, let's just think of it as an open cylinder, and it's got this plunger type thing that just fits. Maybe there's some lubricant that means the air can't just move around it. So, you know, you could actually move this piston up and down and cause the gas inside of this container to compress more or less. You know, to look at this kind of situation from the point of view of you know, Newton's three laws, we end up doing things like this. We say, well, there's a force. If there's a gas inside and we push the plunger down and we compress the gas, the gas pushes back on the plunger. It gets harder and harder to push it down. And so there's a force on the plunger. And what's causing the force on the plunger? Well, it's a contact force. The gas is exerting the force. And you know what? If we look at the size of the face of the surface of the plunger, the area of that, and we take we could even think, okay, how much force is being applied for each little bit of area? In other words, if you take the force and divide the area, we get the force per area. And you know what? That's the scientific definition of pressure. And so when we think pressure, that's really force per area. And if we want to find the total force on something caused by pressure, we just take its area multiplied by the force. And so then you can apply Newton's laws because you've just got forces again. Okay. Well, these very simple kinds of understandings are what's necessary to come up with things like steam engines and internal combustion engines and things. So it ends up being kind of a big deal. What if we wanted to, you know, try to analyze global warming or something? We might try to figure out, you know, what's happening in the atmosphere, and how would that work? How would we do that with these very simple laws that Newton came up with? And maybe this simple idea of pressure that we've come up with, which can be related to the force. Well, we might just kind of imagine dividing up the atmosphere into little blocks and figuring out you know, like each little block of the atmosphere, how much pressure was on the top and the bottom and the size. And we could kind of figure out, you know, would this block end up being squeezed in or would it end up being shifted, which sounds like wind to me if you got gas moving. It turns out that you can take Newton's laws and simple definitions about pressure, which are just definitions that are convenient, and you can apply calculus and you can actually describe the weather. Okay. Well, as we said, you can take Newton's laws and you can talk about waves. Like if you just look at a little wave, you can like in some places the water is a little higher than the normal surface, in some cases a little lower, and you can figure out, okay, if maybe I'll divide up this water into little columns, and I'll ask what would happen, if I analyze each little column of water, given the fact that it's, positioned where it is because gravity is going to pull on it, and then you can figure out all kinds of things. Similar kind of thing with sound. You can figure out how that, like, let's say you've got a tuning fork and it's slamming, it's pushing on air as it vibrates and causing air to be denser, but then it's all vibrating back the other way, and it's causing air to be less dense, and you end up coming up with something that's a lot like water waves, except this is called a compression wave, and it's handled by the same mathematics that Newton came up with. So you can describe sound, and Newton was able not only to describe sound, but he was able to even mathematically figure out what the speed of sound had to be in the air, depending on, all kinds of things like the gases, like what's in the air, like oxygen and nitrogen, and what the temperature is, and things. But he was able to figure that out from math and his basic principles. You could take a guitar string or like a violin string, and you could divide the string up into little tiny pieces, and you could analyze the motion of each piece, and you could determine that when you plucked a string, that you would end up with a vibrating wave that would be at one or another of a set of frequencies that were possible on that string, and you could figure out how that string tied to the sound that it would produce, and you could fully explain it. Okay, so all of this vast understanding of all these very different things, it all goes back to understanding Newton's three laws. Now, Newton thought of everything. So he was also a big, he was a big fan of astronomy. He invented a whole different type of telescope, which used a focusing mirror instead of what's called an objective lens, and his telescopes were much lighter and easier to handle. He did various studies on light. He used a prism to divide light into its component colors, and then he was clever enough to use a prism on some of the light that had been divided by a first prism to see that it didn't divide further. So he ended up thinking that light was made out of particles. He had arguments with Huygens about this, who was still around, and they did not see eye to eye on this. But yeah, Newton contributed a great deal to the study of optics and to to understanding light. We're not even beginning to reach the end of what you can do with Newton's laws, but now I'd like to examine some other cases that help us get to another important aspect of what we can see from them. If we look on the left, we see a pulley system. Okay, so we have this pulley, and from the whole set of pulleys hangs this weight called W down at the bottom. Well, now if you just think about it, if you pull this rope, kind of over to the side where you've got this arrow pointing down that says F, if you apply this force to the rope and you pull the rope down, like if you pull the rope down 1 foot, the you know the, all that rope you're pulling, that whole 1 foot of rope is coming from the rope that's inside that pulley. And so the rope, basically, you've got three, as the rope loops around, each kind of branch of that rope in that pulley system is going to get smaller when you pull the rope and apply force F. So if you pull, let's say we pull out not 1 foot, but let's say we pull out 3 feet of rope. Okay, that means all 3 strands of that rope shown in the pulley system, which has some tension in it, T, all 3 strands of them are going to have to get, or all of them are going to lose like a foot of their length so that you can pull out 3 feet of the rope. Okay, so you're gonna pull out 3 feet of rope, applying a certain force to it. Now this force that you're pulling on the rope is going to be the same as the tension in the rope, because it's your pulling on the rope that's causing the tension in the rope. And this same tension in the rope is lifting up on this weight down here at the bottom. But notice you got three strands of the rope pulling up on this weight, that each pulling with an amount of force T, which is the same as the force you're pulling on the rope with. So actually what the pulley does is, if you're pulling with a force of 100 pounds on the rope, it's actually able to lift 300 pounds, right, in the pulley, because each strand of the rope is exerting a force on the lower part of the pulley, which is attached to that weight. And at this, each strand has the same force that you're pulling with. So this is an interesting thing. So if we pull out 3 feet of rope, right, with a force of 100 pounds, we're gonna lift up a weight of 300 pounds by 1 foot. So maybe we would notice there that, if you and actually in my text there, I pull out one foot and I lift the rope in, the weight lifts 4 inches, but don't worry about that. I'll keep with the whole feet. If we pull with 100 pounds of force over 3 feet, we lift 300 pounds by 1 foot. You notice the multiple of those two, if you multiply those things together, they're the same. So 100 pounds times 3 feet is the same as 3 times 100 pounds times 1 foot. So you can pull with 100 pounds and lift 300 pounds. That's how a pulley works. Okay, that's what a pulley does. So here's the thing. Even though we're pulling at a different force than is being lifted here, that product is the same. And so what we end up doing here is saying, well, let's define work, and this is just a mathematical definition again, and so it may have more or less relationship to what we normally think of as work, but in physics we say, let's define the work as the force times the distance. So the work we do on the rope is the force of 100 pounds times 3 feet, whereas the the work done on the weight is the distance the weight is moved times the force of its weight pulling down, and those end up being the same thing. So when we start seeing these things being the same thing, we might think back to momentum and wonder if we've got some kind of conservation law here. And it turns out we kind of do. But let's think for a moment. Let's try to enlarge this concept a little bit. Where does the ability to pull the rope in the first place come from? Well, we're doing that work with our muscles, but where do the muscles get the ability to do that from? And so what we might say is internally, inside of ourselves, we have the ability to do this work. And where does that come from? Well, we need to eat to stay strong so we can pull ropes and lift things with a pulley. So we would say that the energy we have inside of us from eating, and I haven't really defined that very well, but we would say that gives us the ability to pull the rope. And so what we're going to do is we're going to say that the internal energy we have to pull the rope, that's equal to the work we can do. We're going to define energy as the ability to do work. So work is going to be defined as force times distance, and energy is going to be defined as the ability to do work. So when we do work, it must come from somewhere, the energy to do it. In our case, from inside of us, our internal energy that we got from food, and it's going to be equal to, the amount of energy we use is going to be equal in size to the amount of work we actually do. And whatever energy remains is, it's still the ability to do more work. Well, okay, shifting to a slightly different point on this same topic here. What if instead of us pulling the rope, we put a 100-pound weight at the end of the rope to pull up the 300-pound weight? We could do that. So apparently a 100-pound weight would be able to pull up the 300, through the pulley system, would be able to pull up the 300-pound weight. So that must mean that the 100-pound weight has the ability to do work. Well, how so? I mean, it doesn't eat food. It doesn't have muscles. Well, because the 100-pound weight is being pulled on by gravity. It's really gravity that's causing the 100-pound weight to pull on the rope in the pulley and lift up the bigger weight, which is, so gravity, there's the ability for that weight to do work because, it can be pulled down by gravity. And so we are going to end up calling that energy as well, because it's the ability to do work. We're going to call that potential energy, because something that's higher up potentially has energy as it moves down to do work on something else. So we're going to call that potential energy. Okay. Okay. Let's take these ideas and go back to Galileo dropping lead balls off of the Leaning Tower of Pisa. Can these balls do work? I mean, they're kind of high up, so they have potential energy. So we would think so. It would seem they could do work, like if you tied them to a pulley. What happens when we drop them? Well, they pick up speed. So as they drop, they have less and less potential energy because they're not as high up. They can't do as much work. They're losing the ability to do work as they drop, but they're picking up speed. So is that some kind of ability to do work? Well, yes, it turns out it is. I mean, just the weight of something can pull down on a rope and do work, like on a pulley, but also something that's moving can yank on a rope. So it turns out the motion is a type of energy as well, and we call that kinetic energy. Okay, and then finally, the thing gets all the way to the bottom. Well, let's suppose there's a trampoline at the bottom, just so we can visualize um, what happens. Well, the ball gets fast, the lead balls get faster and faster. I'm just going to worry about the one hitting the trampoline. The lead ball gets faster and faster, and eventually it hits the trampoline, which is rubber, and it kind of stretches out the trampoline until the ball stops, the lead ball stops, and then what happens? Well, then the trampoline is going to kind of reverse the process. It's going to it's going to snap back to its original position, and it's going to flip that lead ball back up in the air. But let's just think about the moment when the cannonball is, completely stopped and has pushed down on the trampoline and is getting ready to be pushed back up. At that point, the ball's not moving, so it has no kinetic energy. It's lost its height, so it's lost its potential energy. Where's the energy now that can do work? Oh, the energy now is in the trampoline. The stretched trampoline has internal energy, and we see that actually being given back up when it, when the trampoline tightens back up and tosses the ball back up in the air, giving it back its kinetic energy. And then it goes, if it was a perfect trampoline, and we didn't worry about the air causing the cannonball to slow down, it would go all the way back to the same height it was before. And we see how, so what we have here is we have potential energy turning into kinetic energy and eventually turning into the internal energy of the trampoline, which is giving up the energy and causing the ball to go back the other way, by moving it up, and so it has kinetic energy, which it loses until it gets all the way back to the full height, and then once again it has the potential energy. So what we're able to see here is conservation of energy. This is another big concept in physics. So before we talked about conservation of momentum, now as we think through these different things and we define work the way we do, and the energy, and we define energy as the ability to do work, we see that there's a conservation of energy that occurs, that as motion, the capacity to do work goes into one form or another, and it relates all the way back to eventually being able to do work. We see that doesn't change, and so we have this idea about conservation of energy, a really big principle. Now, in real life, things do slow down. They do encounter resistance. Like if we gently roll a ball on the floor, it doesn't go on forever. It eventually stops, even if it's a nice flat surface. Why does it stop? Well, what does Newton's law tell us? It says an object remains at rest or in motion unless a force acts upon it. So Aristotle, I'm having a little fun with it here. Aristotle, we've got Aristotle picture saying, aha, I was right, because Aristotle said that things didn't keep moving, whereas Newton says they do keep moving unless a force is acting on it. So Aristotle might think, I've got Newton now, see, things stop. And so Newton can't be right. But, Newton has an easy response to that. He said, well, if they stop moving, I guess we have a force then. The force of friction. Good observation, Aristotle. So, yes, but there's another question then, isn't there? Like, if we're saying that energy is conserved, if friction causes eventually motion to stop, where does the energy go? Okay. Well, it turns out friction creates heat. So you can rub your hands together, and the process of rubbing your hands together, which involves friction, creates heat. And so heat is a form of energy. But how do we know heat's a form of energy? Well, heat can cause water to boil and push pistons and generate motion and do all kinds of work in a steam engine. So, um, so Newton's laws apply, but in the real world, we have friction, and it's called a dissipative force because it dissipates the work that it dissipates the energy that can do useful work. But it's still there somewhere in some form, even if it's in the case of heat. Well, um, Aristotle might not like that if he thought he had Newton over a barrel, so maybe we should just let him have a moment. But how is it that friction creates heat? That might be a question we can ask. So um, downstream from Newton, people did ask that question. At one point, they thought heat was something inside of an object that eventually kind of came out like some kind of fluid. And they thought that because, like, if you start a campfire and you take a log and you put it on a campfire, you can get a lot of heat out of the log, but eventually the log's all burned up and you're not going to get any more heat. So they thought there was a fixed amount of heat inside an object. But then an interesting observation tipped off a scientist named Benjamin Thompson, who was an American, that wasn't quite right. And what he observed was that when they drilled the hole in brass cannon, like they'd have a bunch of horses turning a turntable and through a bunch of gears and everything. They would literally be drilling out the cannon. That it created an enormous amount of heat. And and as long as you kept the horses going and they kept drilling out the brass, you would get more and more heat. And it didn't seem to be a case of the brass just having a particular amount of heat capacity, a particular capacity for heat. And so he figured out that that the work being done. So this is yet another example of conservation of energy. The work being done on the cannon itself was just turning into heat energy. We then had a man named Joule, who was a um, great scientist and also a great Christian. We had him say, well, gee, how much heat does a given amount of work produce? How much heat? So he actually arranged this little apparatus where he allowed a weight to drop, and he can measure the drop. So he can measure the change in the potential energy because he knew how much distance the weight moved, and it pulled a string that turned some paddles inside this liquid barrel, and he measured the temperature of the liquid, and he was able to see how much the temperature would change in the liquid based on how much the paddles whipped around the liquid, and the energy for the paddles was coming from the weight that dropped down. So he figured out what was called the mechanical equivalent of heat. By the way, there are many ways to measure the amount of heat energy. We've probably all heard of calories, but in his day, it was, or at least nearer to his time, they measured energy in something called ergs, ERGS, which is still used in astronomy today, but it doesn't matter. We can convert from one thing to another. So we have heat energy being shown to be an equivalent of so much mechanical energy or potential energy. Um, well, I should point out that this conservation of energy, as well as the conservation of momentum, they actually come from somewhere. Newton didn't know that. Descartes didn't know that. Someone who finally figured out why is it that we have conservation of momentum and why is it that we have conservation of energy. There's actually a lady mathematician named Emily Noether, and she, despite all the barriers that existed at the time, became a professor and did some of the greatest theoretical work in all of physics when she realized that the basic reality of having space where the laws of physics didn't change from one place or another, or depending on one person's relative motion or another person's relative motion, in order for the laws of physics to be the same from different points of view, you would have to have conservation of momentum and you would have to have conservation of energy. And so from that we can see that God made a universe. He chose to make a universe where physics would behave the same way, even from different perspectives, because without that we wouldn't be able to make much sense out of it. But her accomplishment actually also set the stage for something called the Standard Model, which we're going to get to later, so we may mention her again. Okay, so just want to recap a wee bit. Last time we talked about the importance of the scientific method in starting, really getting science started and in technology exploding. So Francis Bacon did that. So we had Bacon. We talked today about how heat is actually equivalent to a certain amount of energy measured in ergs. So I've given you bacon and ergs. There it is, bacon and ergs. So that's a lot to chew on. Um, but you know what? Before we leave the Enlightenment, let's talk about dessert. And I want to do that by talking about angel food cake. Okay? Um, it's a science and Christianity class after all, so angel food cake seems to be appropriate. Well, what do you need to make angel food cake? Most people need a recipe, right? So here's a possible recipe for angel food cake. Notice there's a certain amount of white sugar in here, 1.5 cups. Well, what happens if we use, just a little less sugar, like 1 3/8 cups? So like an eighth cup less. Or what if we make it a little sweeter and we do 1 3/4 cups, so an extra quarter cup of sugar? Are we still going to end up with angel food cake? More or less, you can vary the recipe somewhat before you end up, not achieving the basic result. It's not super sensitive. Baking is probably more sensitive to changes in ingredients than most cooking. Like soup, you can wildly vary the ingredients you put in soup and you still end up with soup. But you can even take something like this and you can vary the sugar a little bit more or less, or the salt a little bit more or less, and you can still end up with an angel food cake. It's just a little more sweet or less sweet, or a little more salty or less salty. It's still angel food cake. Well, um, John Dalton, around 1800 or so, discovered, or he learned, that that was not the case for chemical reactions. Okay, now before we leave the Enlightenment, this is an important topic for us. I will say that Newton never really understood chemistry, so of all the things Newton did, one thing he didn't do was figure out the essential ideas of chemistry. Newton was still dabbling with alchemy, right? But Dalton realized that chemical reactions only worked in very specific ratios by weight. Okay, so for example, if you had 32 grams of oxygen, you could combine that with 2 grams of hydrogen to give water. but you couldn't simply use 3 grams of hydrogen or 4.71 grams of hydrogen if you wanted to fully combine it with 32 grams of oxygen. If you tried, you would either end up with leftover oxygen that didn't react or leftover hydrogen that didn't react. Okay? Um, so there are different ways of combining hydrogen and oxygen, but not to get water. Okay? You know, but the basic idea that he came across was chemicals only combine, substances only combine in certain very specific ratios by weight to give other things when you tried to get reactions going. Why would this be? And Dalton realized that in order for that to be the way it is, it must be that you have little atoms combining into little groups of atoms called molecules that characterized each particular type of substance. And so in the case of water, you have one oxygen combining with 2 hydrogens. And, oxygen weighs a certain amount and hydrogen weighs a certain amount. And so you can start to figure out that by the fact that there are these very definite ratios by weight, when you combine things and get something else in chemistry, you can start to figure out that there are atoms, that things combine in certain ratios because you have certain you really must have atoms. If you could have, if you didn't have specific units of oxygen and hydrogen, it wouldn't be that way. You could just have a little extra hydrogen-y water or a little extra oxygen-y water. But no, that's not what happens. They combine in certain ratios, and so it would seem that there have to be individual pieces of oxygen and hydrogen to explain that. That's what Dalton observed. And you could start also figuring out what the relative weights of one atom was compared to another atom. By the way, he is not considered the father of chemistry. He's considered the father of modern atomic theory because this was atoms based on something. He had a reason for believing this. But the father of chemistry, we didn't talk about him. His name was Lavoisier, but he had noticed before that you had something called conservation of mass. The mass didn't change in a chemical reaction. In Lavoisier's day, they thought it did because, like, if you burned a log on a fire, the ash that was left didn't weigh nearly as much as the original log. But he discovered that if you kept up with all the different things that happened when you were having a chemical change, like you did it inside of a closed container, that all the things added together would still be the same weight. So you didn't lose any mass. And Dalton is able to explain it. It's because you're just rearranging the atoms when you get the when you're having a chemical reaction where you have certain reactants that combine into some different products. And so that rearrangement of atoms explained why you didn't have an increase or a decrease in mass, like Lavoisier answered. Chemistry took a leap forward, and he was even able to start writing chemical formulas. So if any of you remember high school chemistry where you wrote formulas, Dalton's the reason for that. And Aristotle was wrong again. There were, in fact, atoms, and they were not, in fact, just the 4 Greek elements. Mendeleev took this idea and ran with it. Mendeleev was also a Christian. He started arranging the atoms, as the relative weights of the atoms were figured out of the different elements. He started arranging them from lighter to heavier, and then also tried to stack atoms with similar properties together. So as you go from left to right, you're getting heavier, and as you're going from top to bottom, you're getting heavier. But he tried to arrange these chemicals so that they had similar, the chemicals that were in the same row had very similar properties. And so he was able to take almost all the he was able to come up with this table and notice that and he was able to do this because he noticed that the properties repeated periodically. Every so many elements you would start having similar properties again, and so he didn't know why the elements fit into this particular shape when you arrange them by properties, but eventually that would be figured out. But this also was great help to chemistry. He was even able to predict the discovery of certain new elements based on holes in his table where there should have been an element that was between the weights of the two elements on either side, the two atoms on either side, but having certain properties that would be expected. And indeed, they were found later. So that was pretty cool. Um, it's worth pointing out that despite all these triumphs leading from Dalton's understanding that atoms made up matter, scientists didn't. There were some scientists who did not really accept atoms as being a thing. They understood that atoms kind of explain chemistry, but maybe that was just that. Maybe it was just the pattern that fit chemistry, and that didn't mean there were actually atoms. It just meant that the pattern was as if there were atoms. But eventually Einstein was able to analyze something called Brownian motion, which is where very tiny grains of pollen under a microscope would jiggle around, and they weren't alive or anything. So it turned out that they were jiggling around because the molecules in the liquid that was inside them, that the pollen grains were inside, would actually be causing the little pollen grains to bounce around. And he was able to analyze this very thoroughly and show that atoms were really there. And so finally, atoms were widely expected or accepted. Well, if you take all this Newtonian physics and you take the idea of atoms and you start thinking about pressure being actually caused by all these atoms bouncing around inside a piston and pushing on a piston, you're able to start relating things like pressure and volume and temperature to the actual motion of the atoms and everything. And doing this sort of thing helped develop the science of thermodynamics, which enabled efficient steam engines and efficient internal combustion engines to be developed. Not to mention, it ended up being a general science that can analyze everything from refineries to storms. So we have, similar to Newton's three laws, we end up having three laws of thermodynamics and sometimes a zeroth law. Some people talk to. The first law we've already seen, it's conservation of energy. The second law is something called entropy. It's a tricky thing to explain. It has to do with how many different ways you could arrange a system, and it tends to always increase. And then you have you end up in this science finding that there's kind of an absolutely lowest temperature you can reach. Okay, so those are the laws of thermodynamics. So let's just sum up our whole class. Overall, if we compare the nature of Aristotle's theories about motion to Newton's, aside from just being wrong, we see that Aristotle's theory is not as good as Newton's theory because it's entirely qualitative. It's just words. There's no way to get numbers out of his theory. You can't predict or understand what measurements should be. It's philosophical. It's not mathematical, and that turns out to be the key problem with doing experiments against it, and that turns out to be the key reason why Newton's approach to describing motion succeeded. Um, Aristotle's statements are just broad; they're hard to apply to a particular situation. It's hard to take complex situations like violin strings or waves on the water and break them into little pieces and understand what you would expect. So none of that works with Aristotle. Okay, and never mind the fact that he thought different rules on Earth and in the heavens occurred, and that was just kind of his assumption, and and there's no generalizing from that, you know. So Newton's theory was everything that Aristotle's was not. It was mathematical. He, in fact, invented the math to make it work. His principles were all well defined. They were fundamental. They could be applied to uh, even complex systems because you could look at each part of the thing you were trying to describe and think about you know how each little part would work in relation to the others, applying Newton's laws. So it was a great success, and physics grew rapidly. Um, well, we've been pretty tough on Aristotle so far in this course. I do want to say a few positive things about Aristotle. Um, you know, in Wikipedia, it says even after 2,300 years, Aristotle was among the most influential people who ever lived. He contributed almost every field of knowledge then in existence, and he was the founder of many new fields. So that's what Wikipedia said. He invented the term logic. He he studied it, he formalized it. He, in fact, was called the first scientist because while he didn't do so great understanding physics, he did some pretty significant work in zoology, and he's still his work in zoology is still considered groundbreaking. Okay, his fingerprints are all over our modern way of thinking. Some credit him too much and even claim that he's the father of the scientific method, but I think that's far from true because he never really got the idea of, you know, confirming your theories and refining them with experiments and you know, coming up with new insights and discarding old ones depending on what the experiments told you. Okay, but he continues to be relevant. You know, he's thought about in political context. He philosophized about ethics. He's still widely studied. In terms of science, I think his most important legacy is that he just had unbelievable enthusiasm for thinking about everything around him, for all of nature, for everything around him on Earth, as well as everything he looked at in the heavens. He was curious about it all, and we can even tie back to our last class discussion. Centuries after his death, the very people who were instrumental in causing the church to create all these medieval universities from which the scientific method sprang, these people were students of Aristotle. They, in studying Aristotle, who had all this enthusiasm for studying everything around him, they pushed to the founding of these universities. They were part of what was called the scholastic movement inside the church. So Aristotle actually had a big role in modern science eventually happening. It's just he didn't get it right himself in every respect all the way back then. But, you know, pretty impressive what he did do. Now, I do have a parting comment that's more of a spiritual um, note that we can, or a spiritual lesson we can learn here. You know, and it's all centered on the Bible verse that tells us to test what is good, to hold to what's good. Aristotle, no doubt, was an intellectual great, but he did not always read the book of nature very well. Now theologians still study and apply Aristotle's philosophy. As I say, it's not a bad thing. A lot of good has come from it. But no human thinking is perfect. Not Aristotle's, certainly not mine. Okay? Some things that seem wise, like Aristotle's physical theories seemed wise for so many years, are in fact vain. They're empty. They have the appearance of wisdom, but they're not correct. In the same way, you know, Jesus rebuked Jewish scholars of his day for missing the whole point of Scripture because they were so dazzled by the brilliance of certain rabbis who had philosophized about what Scripture meant. So they'd build on top of you know, one rabbi had built on top of another rabbi's traditions, and it just eventually got away from the whole point of Scripture. So we could compare that to the Apostle Paul's reaction when he was teaching out of Scripture. In Berea, the Bereans you know, they didn't take Paul's word for anything as being authoritative, but they ran home and studied for themselves and kind of confirmed everything that Paul was teaching them. And Paul commended them for that. So they tested what Paul said. You know, the Holy Spirit can guide us into all truth, it says in John 16. So we need to test. Right? Just like the scientific method test, we need to test. We need to prod. We need to think through. We need to try to see if in any way our thinking is broken. We need to test. We should remain teachable. We shouldn't be dismissive of other people's views, but we should test those views. We shouldn't just accept them as an authority, because then we're just you know, we're not really confirming truth. We're not really testing it. So we should ask God for wisdom and discernment. We should test claims and hold to what's good, whether it's in the realm of science or whether it's in theology. So bottom line is, testing is part of the scientific method, but it should also be a part of everyday Christian life. Okay, so that's it for today's class, and for our next class we're going to have some shocking physics. We're going to talk about magnetic personality, and we're going to keep our eye on the clock. We'll be able to microwave our leftovers from today, maybe some of our bacon and eggs and angel food cake. We can catch some rays and enjoy a little Maxwell House as relate to one another for a day. It won't be boring, at least not yet. But after next week, uncertainty enters into the class. Thanks for listening.